Let's give it up for Sherwin and his team. At this time, we're going to move on to the next team, which is the Georgia Tech Institute of Technology team. I wanted to take as they are coming up, I did want to mention a couple of things, and I think the fact that we have so much experience, I think, with our judges and actual feedback directly from Cuba is really exciting to see that here today. In the past, I think we've been able to look at the engineering side and the actual application of these technologies and projects can be very well vetted, so we appreciate that coming in from the judges. So this team is going to be presenting specifically on the implementation of micro-catchment systems in Cuban agriculture. So Ajay and his team have the floor.
Good morning. We are Yellow Jackets for Cuba, a team of first-year students from Georgia Tech. My name is Ajay Sukwani, and I'm pursuing a bachelor's in mechanical engineering.
Hi, my name is Kinara Banda, and I'm pursuing a degree in material science engineering.
Hi, my name is Varnita Prakash, and I'm pursuing a bachelor's degree in aerospace engineering.
Hi, my name is Duncan Siebert, and I'm pursuing a bachelor's degree in industrial and systems engineering.
So today we're going to talk to you about the implementation of micro-catchment systems for agriculture in Cuba. As we get started, we want to talk about what the problem is. As we all know at this point, there have been a lot of extreme weather events in Cuba, starting with the drought. And at this point, about 43% of the territory has been affected, as of our statistics from 2017, which means 900,000 people are without sufficient clean water. This classifies as the second highest tier of drought, which is extreme drought. And with climate change, these extreme weather events are only going to increase in occurrence, whether that's drought or floods. And as this happens, agricultural water is scarce, and food and export production is low. You can see from our chart here, the PDSI shows the index of droughts over the years, and the red section on the end kind of shows the increase in frequency in the recent past. So the question we asked ourselves is, how might we provide Cuban farmers with an affordable, effective, and personalized solution during periods of critical water supply? Some of the things that already exist for the territory here kind of shows the crop distributions across the island. So you have tobacco, rice, and coffee that we focused on here that you can see are distributed across different elevations and slopes across the island. We wanted to create a solution that would be applicable for all of them, and that's what Kinara is going to talk to you about.
So because of the fact that the major crops, tobacco, rice, and coffee, are grown in different regions with different slopes and different soil profiles, we figured that the rainwater harvesting system of the microcatchment would be the most effective way, because it could be personalized and it could be customized for every different crop type and soil type and also the slope. So a microcatchment system is basically a contoured area with slopes and beams, and what it does is that it increases the runoff collection from the rain and stores it in the soil profile. The length is generally between 1 to 30 meters, and some of the advantages of a microcatchment system compared to other rainwater harvesting systems is that it enhances even plant growth, and it's easy to construct, given the length is between 1 to 30 meters, and it's not site specific. So if the terrain is irregular, it can be constructed around it, and it also maintains the saline balance, maintaining the soil fertility. So there are multiple types of microcatchments, like the negarim, the contour bunds, the semicircular bunds, and the contour ridges. And depending on the slope, the crop type, and the soil type, they can be selected for different crops. So the process of selecting an optimal microcatchment system, we require the slope to be less than 5% and the infiltration rate of the soil to be less than the rainfall intensity. So what you see here is a basic flowchart that helps us to determine the optimal microcatchment system for a particular crop type, soil type, and also a slope. We also consider various social economic factors because we want a personalized solution for the farmers to use. And so we require the participation of the farmers is also a really important factor. The adoption of the system, the ease at which these systems can be adopted and implemented, and also the area differences is also what we look into. So after we determine the optimal microcatchment system, we also need to find out the microcatchment size, because the difference in the annual rainfall and the water requirement of the crop helps us determine the optimal microcatchment size in order to maintain or cope up for this difference. So the main data that is used in determining the size is the hydrological data, which includes the annual rainfall, the terrain properties, etc. The soil infiltration data, and the runoff coefficient, which is specific to every soil type. The annual rainfall of that particular region, that's the terrain requirements. The other crop requirements that we also incorporate is the crop water requirement, the crop factor, which includes the transpiration and the evaporation from its soil surface and from its leaves, and also the reference crop evapotranspiration.
So as for our initial implementation, we were looking for two important factors when we were deciding on focusing on central Cuban rice farms. The first was which crop would be the most benefit from a microcatchment system. So we looked at what different water requirements are for crops, and because rice is the type of plant that requires constant sitting water or stagnant water, we felt a microcatchment would be extremely beneficial in this specific field. The next thing we did is we looked at what areas rice is grown in throughout Cuba. We found that they're grown in the central part of the island as well as the left and rightmost points. The problem with the left and rightmost points is that those are very mountainous regions, so it's a little more difficult to achieve this 5% gradient, whereas the central region is more of a flat field. So we found that the labor cost for implementing microcatchment here would be extremely easy and very cheap and effective, which is why we chose this as our initial stage. We plan on using a variety of sensors and drones to take our moisture and topography calculations. And what these sensors and drones will do is gather all of the different coefficients that we need to develop the ideal microcatchment system for the farmer, so that the farmer can then decide, or at least know what microcatchment system they would need to set up in order to increase their rainwater collection. And we plan on outsourcing that using big data analytics so that we can model it for a variety of different crops throughout the island. And we actually spoke with the CEO of Civotech, a data analytics company, to discuss the feasibility of implementing our software and algorithm. And we found that it can be done at a relatively low cost and with a fairly high amount of success. So here we have a very basic layout of what our final product would look like. On the top, the only inputs by the farmers would be the crop, the location, and the soil type. And then it would have all of the data analysis here on the left side, which the user or the data analytics company can use to verify that the software and algorithm is all running up to par to whatever the reality is in their situation. And the image would show a basic diagram of what kind of microcatchment system would be ideal for their scenario, along with the basic description of the ideal microcatchment system and the area that they would need.
So now we're going to move into the cost analysis of our solution for a second. And the first and foremost cost is, of course, the database, the development of the algorithm, and the analysis of the data collected by the probes. And this will be outsourced, of course, so we can take advantage of existing human capital and fixed factors of production. And for our initial pilot project, we have a quote of around $5,000. And the next factor would be the implementation cost of the microcatchment systems, which would be monetarily non-existent, but would involve some amount of labor from the farmers. The maintenance cost is similarly non-monetary and may just involve small amounts of labor by the farmers. And the probes themselves may cost from around $150 to $550 based on quantity and quality. And the same goes for the drones, which range from $3,000 to $5,000. Now, the farmers have to access our app or web app through some sort of platform. And the most recommended platform would be a mobile phone, which, looking at the lower end of the spectrum, would range from $60 to $100. Although they could also easily use an internet cafe or a laptop if they had access to one. And this brings us to our next point, internet infrastructure in Cuba. Since 2018, actually, mobile internet has been available in Cuba, but is prohibitively expensive, so that farmers would not be able to afford it. However, we're hoping to partner with the Cuban government to perhaps subsidize or even provide freely internet to farmers partaking in the pilot program. And so this brings us to a total cost range of $8,210 to $10,650 for our initial pilot project. But it's important to keep in mind that the drones, for example, is an initial fixed cost that can be reused, and the same goes for the probes. And to some extent, much less data analysis will be required after the initial period of time in which the algorithm is developed. So the $5,000 are not some sort of steady fee that has to be paid over time. So now we're moving on into the economic impact of our solution. It will increase food security, which is, of course, an indicator of human development. And in many cases, increased food security leads to increased economic growth. It will also decrease soil erosion and maintain a balanced soil fertility, which will increase the quality and quantity of the crops grown by farmers. And initially it will have a great effect on imports, as Cuba currently imports around 75% of its agriculture. And so by allowing Cuba to grow more rice and other crops on its own, it will reduce the trade deficit and enable it to become more self-reliant. And if our project scalability succeeds, we can also scale it to tobacco and sugar, which are sugarcane, which are some of Cuba's major exports, leading to increased export profits and, again, a decrease in the trade deficit. It will also result in less reliance on irrigation systems, which will allow Cuban farmers and the agricultural industry to weather extreme weather like droughts more efficiently.
So to sum up our overall idea, we want to implement microcatchment systems throughout Cuba. We came to this solution because we found microcatchment systems to be a very cheap and effective form of increasing water retention in places that are affected by severe drought. In order to kind of innovate and revolutionize the implementation of microcatchment systems, we hope to use topographical and hydrological data to scale the project, not only by giving farmers a model of what they should implement in their system, but to scale it towards multiple crops and multiple locations around the island. And in order to effectively do that part of our solution, we plan on using big data analytics as well as AI to model the different scenarios throughout the island of Cuba. And as far as future plans, like I mentioned before, we want to increase our scale. One thing to keep in mind is that since we are using AI and machine learning, this algorithm would continue to improve upon itself as it gathers more data from different locations on the island. And by continuously improving, it would provide Cuba with a continuous return on investment, and it would provide it with an increasingly perfect solution or increasingly perfect model. And we also want to increase the ease of access of our user interface and make it more intuitive for farmers, because we know a lot of these farmers might not have access to the amount of technology that we did as kids. They might not be as sophisticated or tech savvy per se, so we want to make sure our platform is very easy to use.
We'd like to thank Dr. Jeffrey A. Davis, who's our faculty advisor at Georgia Tech, as well as Pete Martinez, who is our advisor from CISC.